Welcome back. In this section, we are going to talk about the robust deep and inductive anomaly detection techniques proposed. So let's get started. Just recapping the definition of anomaly detection and actually what are anomalies. Anomalies are objects different from most of the other objects. Yeah, just like this red apple, which is quite significantly different from the rest of the green apples. And anomaly detection is often applied on unlabeled data, which is also known as unsupervised anomaly detection technique. Anomaly detection has two basic assumptions, like anomalies only occur very rarely in the data, like the red apple here, which is just a single item amongst many of the green apples. Well, coming to the application of anomaly detection, a typical application would be a video surveillance system detecting background activities within a given scene. Today, stationary cameras are extensively used for video surveillance systems, and video surveillance is employed in many applications such as car and pedestrian traffic monitoring, human activity surveillance for unusual activity detection, and also people counting, etc. A typical surveillance system consists of a moving object detection, object tracking, and high-level motion analysis. It's very important, to detect the regions of corresponding to moving objects, especially with respect to people and vehicles. As shown in the slide, here is a scene. Here is a restaurant scene. The top row shows some activities, and the second row shows when there is no activity or there is no movement of people around the given area of the restaurant, and thus it would be critical to identify what are the background activities, or what if any objects are, if any people or any object is moving within the area of surveillance. Yeah, this is one of the most promising applications of anomaly detection, and especially the robust anomaly auto-encoder based technique has been applied to the restaurant data sets, which I'll be discussing later on in the slide. The key idea is to find the combination of attributes which capture the bulk of the variability, which captures the bulk of the variance, and hence these set of attributes which are identified can explain only the normal data very well. So the key idea here is the combination of attributes, to obtain the combination of attributes which explain the bulk of the variability. Several methods use principal component analysis, the top few principal components in this case capture the variability and hence the normality of the data, whereas the outliers have the variability in the smallest component of the PCA. And let's look at some of the motivations and challenges of applying PCA technique, PCA as technique, which is one of the spectral technique applied. Anomaly detection through PCA is highly sensitive to data perturbations. Like you can see on the figure on the left here, there is in the absence of outliers or anomalies, the first component captures the bulk of the variability of the data, and hence it is assumed to explain the data well. In the presence of outliers, the variability may not be explained very well. So hence the PCA is very sensitive to data perturbation. And PCA, and hence to overcome this limitation of PCA, a robust version of PCA was proposed and shown to perform well, but the robust version of PCA fails to capture the nonlinear projections within the data. And if the data is highly nonlinear, PCA as well as the robust PCA fails to capture the nonlinearity present within learn the nonlinear structure present within the data. So hence we propose a robust autoencoder, and if we are dealing with images, we can adapt it to a convolution based autoencoder approaches, robust approaches, and that is the primal focus of our discussion in this section. So let's look at the related works for the same. So as discussed, anomaly detection is basically an unsupervised technique, and it has been approached by applying non-parametric and techniques such as using one class of the data, which is one class wherein we only have the data related to the healthy or the normal data, and techniques such as one class SVM have been shown to perform well in this scenario, and also the matrix factorization based approaches are also shown to perform very well, and the proposed robust autoencoder method mainly falls to the category of matrix factorization technique. So let's take a quick review of the matrix factorization approach. PCA can be interpreted as a matrix factorization approach, wherein we factorize the input matrix X with the dimensions input matrix X with belonging to a real dimension of n cross D, wherein with the dimensions n cross D, we factorize the input matrix X of the dimension n cross D into a Z matrix and the weight matrix W, and which is then formulated as a minimization problem to reduce the reconstruction error. Comparing it to the original input matrix, as shown below in the equation, we could obtain the weights, we could solve for the weights W. And the main limitations of this approach is that it is linear, and as discussed before, it fails to capture the variability in the presence of outliers, and hence it is very sensitive to data perturbations, and it does not capture the nonlinear projections within the data. So hence a robust PCA version has been proposed, which generalizes the PCA with the tuning parameter of lambda. Intuitively, the signal S is the signal matrix, and N is the noise matrix. The points with high value of N are considered to be anomalous, and yet again, this robust version of PCA fails to capture the nonlinear structure within the data. So extending these approaches to auto-encoder based robust versions, both the normal as well as the convolution auto-encoders, to move towards the robust autoencoder version, let us give a brief introduction about the autoencoders, and moving on, we will formulate how we come up with a robust version of the autoencoders proposed for anomaly detection. So consider an autoencoder with a single hidden layer, as shown in the equation 2, where X is the input matrix, and F is any nonlinear activation function which is chosen of choice, and where the U and the V represents the weight matrices from the input to the hidden, and ultimately the output from the hidden to the output layer. The V matrix corresponding to from the hidden to the output layer. So here X hat, which is F of X of U times V, is the reconstruction error measure, and XU projects the X into k-dimensional space, and the U matrix, which is real matrix of dimensions D cross K, and V is again the weight matrix from the, as discussed before, from the hidden to the output layer, which is of the dimension K cross T. And choosing a nonlinear activation function such as sigmoid helps to capture the nonlinear variability within the data. Well, as discussed, the U is the weights from the input to the hidden, and V is the weights from the hidden to the output. And activation function F, which tries to map the input to the output using a suitable activation function, and hopefully captures the nonlinearity present within the data. This slide explains the comparison of conventional anomaly detection methods, and it has been classified into three. We try to categorize and discuss as to how we could handle the data perturbations, and Well, this slide presents the comparison of the conventional anomaly detection methods with respect to handling the data perturbations, capturing the nonlinearity structure within the data, and as we can see, the proposed autoencoder, robust autoencoder based approach is capable of handling the perturbations and also capturing the nonlinear structure present within the data. So moving on, from autoencoder to a robust autoencoder approach, consider for an activation function f, for some non-decreasing activation function f. Now consider the following objective, which combines the salient elements of the autoencoder discussed before, and where f dot, where f, the function f, is understood to be an element where f times x of v is the reconstruction error measure, and lambda mu are the tuning parameters, and z, which is the latent representation, which is obtained through applying the function f times x of u, decoded by the weights v. And here n captures the gross outliers, and lambda, when lambda equals infinity, we get n equal to 0, and the model reduces to a standard autoencoder equation. And when lambda equal to 0, the one possible solution is n equal to x, and u, the u and the v matrices being 0, so that the model memorizes the training data. For intermediate values of lambda, the model augments the standard autoencoder with a noise absorption term that endows the robustness. So here we include the n term by introducing a regularization parameter lambda. We are hopeful of introducing the robustness into the normal autoencoder equation. Well, comparing the robust autoencoder with a robust PCA. Well, from the equation 4 and 5, the conceptual similarity between the equation 4 and 5 has been established in the paper published. So for more theoretical approach for formulations of comparison between these two techniques, you can refer to the paper for more details. Well, with respect to training the robust autoencoder or robust convolution autoencoder, the objective function of the model, both the equation 6 and 7, is non-convex, but unconstrained and sub-differentiable. There are several ways of performing optimization. For example, the differentiable activation f, one could compute subgradients with respect to all the model parameters and apply backpropagation. However, to leverage existing advances in training deep networks, we observe that for a fixed value of n, the objective is equivalent to that of the standard autoencoder on the matrix x minus n. Thus, one can optimize the parameters theta of the model using any modern stochastic optimization tool for deep learning that exploits gradients such as the ADAM optimization technique. For a fixed value of theta, that is u and v in the standard autoencoder case, the objective is solvable via a soft thresholding operator on the matrix x minus of x hat of theta here, and where omega is considered as any regularization function. And here we can see that the equation 7 is non-convex but unconstrained and sub-differentiable as previously stated. So for a differentiable function f of x theta, the backpropagation is employed, and we follow a soft thresholding approach to optimize and obtain the value of n. For a fixed value of n theta, u and v, the objective could be rewritten as shown in the equation 8, and applying the soft thresholding to compute the n is shown in the equation 9, wherein the difference between the x and x hat of theta minus lambda by 2 if the value of x minus x hat of theta is greater than lambda by 2, or x minus x hat of theta plus lambda by 2 if x minus x hat of theta is less than minus lambda by 2. So applying this simple soft thresholding technique, one could infer the value of noise present within the data. And discussing more about the experimental setup, we compare all the methods what we proposed, the autoencoder as well as the robust version of the autoencoder on 3 real-world datasets for anomaly detection. Firstly, the restaurant dataset comprising of video background modeling and activity detection, consisting of snapshot from the restaurant activities, and the USPS dataset comprising of handwritten digits, comprising of digits from 0 to 9, and CSIRO 10 comprising of 60,000 samples of 32 by 32 color images pixels of 10 classes with 600 images per class. And the table shown here explains the features and the set of anomalies which were used within the experiments. And in the restaurant data set, one could observe that the feature dimension is quite high, whereas the USPS dimensions of the data considered is comparatively lower when compared to the other data sets. And the way we are forming the anomalies is like we are picking up the images of the cats, and like 50 images of the cats can be considered as anomalous among 5,000 images of dogs. And similarly, in case of USPS data set, the images of ones can be considered as normal, and the images containing 7, which has a close representation to that of 1, can be considered as anomalous. In our case, we consider 11 digits of 7s to be anomalous being present among the normal values of 1s. So the methods what we compared in the paper, robust inductive anomaly detection technique, are the SVD, the robust PCA version, and the robust kernel PCA version, the autoencoder, and the convolution autoencoder where lambda equals infinity, and the robust version of the autoencoder where lambda is any value intermediate value between 0 and 1, 0 to infinity. The experimental settings were conducted for 3 different scenarios, like the non-inductive anomaly detection, the inductive anomaly detection, and also the performance of the methods was validated for the image denoising purpose. In case of inductive, it does not include any anomalous samples into the trained data sets, whereas the non-inductive approaches introduce a small amount of negative samples within the training data set. And as far as the network parameters are concerned, the number of convolution filters and filter size, strides, and convolution operations, and the choice of the activation function was tuned using grid search, and also in few cases where manual selection of the hyperparameters was chosen for best performance. See, the number of hidden nodes H comprises of the number of nodes within the hidden node for the autoencoder or the robust or the convolution robust autoencoder base was chosen again for best performance using grid search. So initial weight matrices were derived for initializing the network weights with deriving from a uniform distribution from -1 to +1. Well, the metrics used for evaluating the techniques are mainly the area under the AUPRC, the area under the precision recall curve, and the area under ROC. And while the AUPRC and the AROC measure the ranking performance, the precision at 10 measures the classification performance, the actual anomalies among the top scored instances. Well, let's take a look at some of the results obtained. So in case of a non-inductive approach, wherein a few set of anomalous images were injected into the training data set. So in our case, we consider 220 images of 1s, which are considered as normal, and the 11 images of 7s, which are considered to be anomalous. And here we could see the ranking of the images based on the reconstruction error. Obtained through R's robust convolution autoencoder approach as well as the robust PCA version. We could see that all the images of 7s have been rightly identified as anomalous in case of the robust autoencoder based approaches. In case of CIFR, we consider 5,000 images of dogs and 50 images of cats are considered as anomalous. And here gives a snapshot of the ranking of the various images comparing the robust convolution autoencoder as well as the robust PCA version. So I could see we could see that all the images of the cats have been ranked correctly as anomalous by our robust convolution autoencoder technique. And this slide presents the snapshot of the metric performance, and the robust RCAE or the RAE outperforms the state-of-the-art methods when compared to the other conventional approaches such as the SVD and the robust version of PCA was compared. And for both the USPS as well as the CIFR 10 data sets, our methods significantly outperformed the other techniques. In case of an inductive approach, the top anomalies images detected are shown here. Comparing both the RCAE and the normal CAE, the CAE approach. So when we say CAE here, we do not include the robustness parameter where the lambda equal to infinity, and where lambda equal to infinity, and which is just as a standard autoencoder. And first train the model on normal set of images considering 5,000 images of dogs, and evaluate it on the test set consisting of 500 dogs and 50 set of cats as considering it to be anomalous. And we could see that the robust convolution autoencoder was having a better denoising was having a better detection performance in this case considered. So we also applied the technique to image denoising to evaluate the image denoising capability. So top anomalous images in the original form in the first row, and the noisy images are shown in the second row. And the image denoising task was applied on the CIFR dataset, and the comparison of the RCAE and the robust convolution autoencoder and the robust PCA version with respect to the mean square error is shown in the chart below. We could see that the RCAE has significantly lesser mean square error, demonstrating its higher capability of performing the denoising of images. So in conclusion, we extended the PCA model to a nonlinear autoencoder setting. So our approach is robust, deep, and inductive, and not oversensitive to data perturbations, and besides capture subtle anomalies. And we could extend the same to various deep autoencoder architectures with sequential data, and in order to capture the sequentiality within the data. And for an example of that would be considering the outlier description. So extending these methods with LSTM based techniques could as well be applied to sequential data as well. Well, thank you. Let us get thank you, and see you soon in the hands-on version of the robust autoencoder based techniques, where I explain the application of robust autoencoder to a real-world application scenario. In our case, we are considering structural health monitoring of the bridges. See you soon.